Transform your optical design process. Go from concept to sales in record time with ZMAX Virtual Prototyping from ZMAX.
Hello, and welcome to today's webinar on technologies and techniques for optical fabrication. I'm Chris Normanshire, the Technical Content Manager at ZMAX. It's my very great pleasure to welcome our presenter today, Jessica DeGroote Nelson, who's Director of Strategy and Technology at Optimax, a leading manufacturer of custom precision optics. Jessica also teaches a course on optical fabrication and testing at the University of Rochester, and today she's going to be sharing some of that vast knowledge of this subject with you. So in a moment, I'll hand you over to Jessica for her presentation. I just wanted to start by letting you know there will be, at the end of the presentation, there'll be a question and answer session where you can ask any questions you have on the content, and also this webinar will be recorded and available offline later. Okay, well, thank you very much. And then Jessica, I will pass over to you to take us through.
Thank you, Chris, and welcome everyone, and thank you for attending today. So it's my pleasure to give a little bit of background of some of the questions that we get quite frequently, two of which are how are lenses made and why is my lens so expensive? So what I'm going to talk about today is how are lenses made, and actually I don't think you're seeing my slides, so hang on, let me go back here. Sorry, we're having a little technical difficulties. Okay. There we go. Hopefully everyone can see now. So the two questions I'll repeat again are, how are my lenses made and why is my lens so expensive? So a summary of what I'd like to talk about today are the first question I mentioned are how lenses made. So what I'll do is I'll go over a really brief introduction to technologies and techniques for optical fabrication and testing. And just 45 minutes, this is going to be a very high level introduction. But I'd like to start with that little bit of background before we start with the second question is, why is my lens so expensive? And I'm going to discuss a few common optical drawing specifications and how they lead to making more cost-effective optical components. As I mentioned today, we're short on time, we only have 45 minutes, so I'm going to focus on spherical optics, and in the future, we'll have time for A-spheres and freeforms on a different day. So let's get started. We're going to talk about making a spherical lens, glass materials, grinding, polishing, metrology, tolerancing a spherical lens for material and fabrication considerations as well as cost, a few final thoughts, additional resources, and as Chris mentioned, a Q&A session. So making a lens. So this photograph here shows raw material as a glass slab, then a ground lens, a polished lens, and then I have metrology mentioned as well because metrology is a very important part of the process. So we'll start with raw material. When you're choosing optical material, as all of you are very much aware, the top two considerations for the optical engineer are the index of refraction and the dispersion, or the Abbe number. Now, I fully agree that both of these values are extremely important. However, there's a lot of additional optical material properties from a fabricator's perspective that are just as important. And I'd like to briefly mention a few of them. Optical, of course, your index and your dispersion. Then transmission, stress birefringence, the temperature coefficient of refractive index, a lot of thermal properties, softening point, thermal conductivity, thermal expansion, mechanical properties such as density, hardness, Young's modulus, fracture toughness, chemical properties such as environmental stability and chemical resistance, and of course, everyone's favorite, availability and cost. Now, I'm not going to go through in detail all of these different properties, but I would like to talk about a couple of them. The thermal properties of thermal conductivity and thermal expansion, and availability and cost. So this next slide here is a thermal infrared video comparing heat transfer of both a metal rod and a glass rod. This is obviously infrared, and you can see the outlines of both of these materials. Now, as anyone can remember, back when they accidentally touched a hot metal pot on the stove, metal conducts heat, and so you're going to see the heat transfer throughout the entire object. Whereas the glass, all of that thermal gradient is localized down by the hot plate, and you can see time is elapsing pretty quickly. So that's something to keep in mind when talking about metal versus glass. We automatically think of glass as an insulator, which is true. However, it still has a thermal conductivity, and we need to keep in mind when we have temperature incident on a portion of it that it's going to cause a gradient. So from an optical perspective, something to keep in mind is that the index of refraction changes as a function of temperature. So it will potentially affect your performance. However, from a fabricator's point of view, glass dimensions also increase with temperature. This is characterized by the coefficient of thermal expansion, or what we refer to as a CTE. I have a little diagram here in the upper right-hand corner that shows this descriptively with the initial volume in purple, and as an object is heated, the volume will grow after heating. This is, as I mentioned, described by the coefficient of thermal expansion. Glass has very unique properties, and at some point in time, at a different time, I'd be happy to describe a lot of these different properties. It's really a very neat material. However, today for the discussion, I want to focus on the enthalpy diagram in the section A. And as temperature increases, the volume increases, and this is going to behave differently for all different types of glass. This is going to happen more rapidly than others. And where this really comes into importance, if you also remember back to the thermal conductivity, if we combine a material that has low thermal conductivity, meaning that there's a very large temperature gradient, meaning that the heat does not spread throughout the material, and the material that also has a high coefficient of thermal expansion, meaning that the volume rapidly increases as a function of temperature, these materials are thermally sensitive, and sudden temperature changes may cause thermal shock or fracture. I have seen and had it happen before to myself, where I have been holding onto an optic that just gets placed underwater and will crack just due to a very quick thermal change. These are things that we need to keep in consideration, and something that may not necessarily be considered when just looking at the index and the Abbe number. So this next slide here, switching gears a little bit into other aspects about the material, looking at an Abbe diagram. I'm fairly certain many of you are familiar with the Abbe diagram, where it shows your index and your dispersion, or your Abbe value, on the two different axes. This is also referred to as a glass map, and many manufacturers offer this in order for optical designers and fabricators, or anyone interested in these materials, to be able to look at all of the glasses available. It's very common to see it in this teardrop shape crescent across the map. One of the very interesting things about this particular glass chart, and this is from the O'Hara Corporation, is that they also give a lot of really great information about the availability and cost. The upper left-hand side shows the availability. This is referred to as the melt frequency, and you can see this indicated with the different colored shapes next to each of the glass types. The next square down is cost, and they have their cost in relative price to SBSL 7. SBSL 7 is a borosilicate glass. It is optically equivalent to NBK7. And as many of you are also aware, BK7 or SBSL 7, they're the workhorse of the optics industry, and fairly benign in terms as well of properties, both mechanical, chemical, and they're pretty much middle of the road optically as well. So it's a really great material. Also one of the cheapest materials and highest production. So moving away from that, it tends to change the optical properties to slightly less desirable state, which I'll mention later, and but also cost it's a good baseline for a cost. So with this, I want to just point out one example on this glass map. When we've surveyed customers before, what is the most popular glasses to use? Most of the responses come back usually with the ones that have the most unique optical properties. And so I want to just highlight two of them right now. They're the SFPL series. These are fluorophosphate glasses, and they are very popular due to their low index and low dispersion, as well as a lot of the other extremes on the glass map. However, they also happen to be more expensive material due to their glass making properties. They just, in order to make them into glass that is defect free, it takes a little bit more effort, so it's more expensive to create the glass. And from a fabricator's perspective, these glasses also tend to be more troublesome to fabricate due to their mechanical properties. They're very soft glasses. Their thermal properties, they're very thermally sensitive, and their chemical properties, they do not have a very good chemical robustness, and they tend to both stain and heat fracture very easily. And so this is just one example that even though in terms of glass may seem fantastic on paper due to its index and its Abbe number, there may be more to it, and a little bit more as to why your optical material might be more expensive. So one of the questions we also get is, where can I find these glass material properties? The manufacturers' websites, the glass manufacturers' websites, are a great place to get the most up-to-date information. You can also find them in glass catalogs or pocket guides, and look for them in preferred glass lists. Many fabricators, such as ourselves, we do keep these right on our website so that we can make sure to update what our preferred glasses are. So going back to the photograph here of making a lens, we've talked, again, very briefly about raw material. Next step up is grinding. So we need to get the material from its raw material state into a near net shape, and how to do that. Well, one of the conventional traditional methods is conventional grinding, and this requires skilled application of relative motion, pressure, and chemistry to grind the optical surface. Reminder of those who are not familiar with the grinding process, the goals of grinding are to rapidly remove material, achieve the desired form, and prepare the surface for polishing, meaning minimal damage. Grinding is a brittle material removal process, so you are essentially creating tiny fractures in the surface. You want to control your grinding process so you know exactly how deep those fractures are. In conventional grinding, surfaces are ground using cast iron or glass tools. In the photograph here, the optician is using a glass tool, and then a loose abrasive, typically aluminum oxide for grinding, in a water slurry. The cast iron is then, with the slurry in between, it removes material off of the glass. Every time you need a different radius, you need to have a unique and dedicated tooling for this. So this causes many opticians and fabricators to have a large array of tools ready for use. And in addition to that, as tools are in use, the abrasive is not only removing material from the glass itself or the test piece, it's also being removed from the tool. And so they require periodic reconditioning. So even though there may be some drawbacks to this traditional method, these traditional processing methods are still very cost effective for producing spherical optics and are used today. And there's a photograph of a similar circumstance of an optic being lapped a couple of years ago. As technology has advanced, deterministic computer-controlled processing has been utilized quite frequently in the optical fabrication process. When I talk about deterministically controlled, it's the ability to both predict and attain a desired result. The CNC process, generation process, utilizes a bound abrasive tool, and I have in the right-hand side an animation that hopefully everyone's seeing okay, going through, and this is a animated diamond ring tool removing material off of a surface and creating a spherical radius. This obviously is optimized. In real life, it does not go quite this fast, but this gives a good illustration of how the ring tool is used to deterministically grind these surfaces. One of the really nice things about these ring tools in this process is that multiple radii can be generated with one bound abrasive ring tool just by adjusting the head angle. So you can increase and decrease by changing the angle at which the ring tool interfaces with the surface. In addition, these ring tools can also be used to generate spherical concave or convex surfaces. This is obviously an example of a convex surface. There are other tool geometries that can be used to generate different shapes. Ring tools are used most frequently for flats and spheres. They're the easiest and most cost-effective. However, there's also something called contour tool geometry. This is and also a different variation of a ring tool where you're using the outer diameter, but it's a single spot transversing across the surface. You can also use a ball tool or several other customized tools. These are used most frequently for A-spheres or for freeforms. And as I mentioned earlier, we'll save a lot of those discussions for another day, but I wanted to at least mention that those types of geometries were available. The next slide here shows just a brief video of these two in motion. This is on the left, it's a ring tool generating, this is a concave surface. So before, when the angle was coming in, it was generating the convex. This ring tool shows it generating a concave surface. And then an A-sphere being generated with a contour tool. So back to our photograph again of making a lens. We've gone from the raw material, grinding. Now let's move on to polishing. So one of the most common ways to polish an optic, especially a spherical optic, is using traditional optical pitch polishing. Polishing is a chemomechanical process. And the goals of this process of polishing are to converge to the final specifications. And what's unique and challenging about this is that we need to converge both the surface form and all of the mechanical dimensions simultaneously. It's something to keep in mind later in this presentation when we talk about tolerancing and why there's different interplays that happen between them, because we need everything to come together all at once, and we need to do this all within a few microns and a few nanometers of precision. Other goals of polishing are to remove all traces of damage. So we have to make sure there's no defects on the surface or any subsurface damage below the surface, and we need smooth, defect-free surfaces. Typically, surfaces are polished with either pitch or polyurethane pads. Pitch is a viscoelastic polishing pad that is really a very unique substance. That the best thing to equate it to is actually asphalt without the rocks in it, because it slowly moves over time, which is one of the things that make it most useful for polishing, because you, as I mentioned earlier, you need to converge when you're removing material, and that slow movement helps both the polishing tool recondition itself in process to make that final surface shape. The slurry that's used to remove material is an abrasive slurry, typically cerium oxide with water. One of the nice things about pitch polishing is that if you have the same radius, multiple lenses can be run on the same tool. This is also referred to as a multi-block. There's a photograph on the left-hand side, or you can polish these as a single. And similar to conventional grinding, these traditional processing methods are still very cost-effective for producing spherical optics, especially when you're running multiple spindles simultaneously. So you get a lot of economies of scale with traditional pitch polishing, and they also produce very smooth surfaces. There's deterministic subaperture polishing. Similar to computer numerically controlled or CNC generation, there's many different methods to deterministically subaperture polish a surface. And when I talk about subaperture polishing, this is a small tool locally removing material. This works using dwell-based algorithms to remove material based on the initial surface metrology and the tool influence function. On the right-hand side, there is a red circle with what looks like a D-shaped spot in the center of it. That is an influence function for magnetorheological finishing, or MRF. And so as this polishing spot moves across the surface, when I talk about dwell-based algorithms, it means that the only thing we are adjusting is time. So we try to keep the removal function as constant as possible, and we are just telling that spot to either spend more time or less time on the surface depending on how much material we want to remove. This results in more predictable surface form convergence than conventional processing. However, because we're using a smaller tool and we're only doing one surface at a time, this can take more time. So it doesn't necessarily offer the overall cost advantage, but you can get much more predictably. So sometimes it is the route to go, even with a spherical surface. One thing to keep in mind, and a topic I will mention only very briefly twice, is mid-spatial frequency errors. These are the residual pattern that's left on the surface from subaperture polishing. These may or may not be an influence on your system, but it's something to consider anytime you're using a subaperture polishing process. On the bottom left-hand side of this screen, there's an example of a MRF, or a magnetorheological finishing polishing run. On the left-hand side within that image, it's before MRF. It resembles the astigmatism, or that you have the potato chip type of shape to it. And what you do is you take that interferogram, plug it into the software, and the dwell-based algorithm would dwell longer on the areas that are high, so on those red spots, and go faster over the blue in order to achieve the desired surface form, which is on the left or on the right hand side. This is after MRF, and you see a much smoother surface that converges to the desired shape. That's an example of MRF, and there's a photograph there. There are several other subaperture technologies that exist. MRF is just one example. Again, I'm not going to go into the details of all of them, but I do have a photograph here of OptiPro's Ultraform Finisher, or UFF, which utilizes a bound abrasive belt on a durometer rubber wheel that also transverses across the surface. And so there's a number of different commercially available technologies, and a lot of companies that have homegrown technologies as well, all that work extremely well and are all varied and have their benefits for different sweet spots of types and materials of optics. So you may ask, well, subaperture polishing, that's one small spot. How is that going to work for a large variety of different optics? Well, a lot of these tool manufacturers have customized their tools to do something very small, down to a few millimeters, up to meter-sized optics. And so there's a large suite of different materials available and machines available to suit the size of optic that fits your needs. But today, one thing I did want to stress is that in modern spherical optics manufacturing, there's not a one tool that satisfies everything. Different geometries, different materials, different specifications, they all require a slightly different processing method. And so what we found is that the modern optics shop is a hybrid of both deterministic and traditional grinding and polishing methods. This is a photograph of a view down one of our lean cells here at Optimax. And it only shows half the cell, but what you can see is a combination of both CNC equipment combined with traditional processing methods. In the end, it allows the optician the ability to choose what is ever best to satisfy the needs of our customers and make that best optic possible. But again, it's a combination, a little bit of new methods and traditional old school as well. So back to the photograph again. Okay, so we've gone through raw materials, we've gone through grinding, we've gone through polishing. Now let's talk about some metrology. So I want to kick this off with a statement that I do love. An optical surface can only be made as good as you can measure it, which I fully believe. You need to be able to verify the surface. I wanted to highlight on here is Professor Daniel Malacara, who wrote an excellent book, Optical Shop Testing. If you do not have this book and would like a reference book on optical metrology, I do highly recommend it. He is in there quoted, "Modern instruments require optical surfaces with complicated shapes and deviations smaller than a fraction of wavelength of light. This is challenging from a fabricator's perspective, but also exciting as we keep moving forward, especially as that wavelength of light keeps getting shorter and shorter that we're working with. So I want to talk very briefly about a couple interferometric methods or testing methods to measure some of these spherical optics. The first being the classic, the Newton interferometer. This is also known as test plating. Test plating is the fastest and cheapest surface test method. This can be done in process and is still done in process here at Optimax today. Those of you who are not familiar with test plating, it's when you take two surfaces, your reference and your test, and there's a photograph of it in the bottom, and they're in contact illuminated by a monochromatic light source, typically green, to produce interference fringes. And when you're looking at this and you're seeing the fringe pattern, you can determine the difference between these two to calculate the surface form of the optic under test. This is a historical reason why most specifications are given as peak to valley, because when you're only detector and your analysis is done by your eye, this is the best resolution that you can do. But moving forward into Fizeau interferometry, this has the same interpretation as fringes as a Newton interferometer, so which led itself very well for integration into the optics fabrication shop. But what was nice about this, and you can see from the image here, is that you have the test and reference surface now separated. This lowers the risk of scratching the test surface. It is always a fear that if anytime you are touching an optical surface, you increase the risk of some type of defect being placed on the surface. There's nothing worse than having your surface almost reaching all of the convergence of all of your specifications and picking up a scratch. So this is something that helps minimize that risk. The Fizeau interferometry utilizes a laser, and hopefully this animation you can see coming through a beam splitter, through a collimator, the reference surface, test surface, and reflecting off of both of those, recombining through into the camera, creating your interference fringes. And then we'll go through a phase shifting in order to capture the information needed for surface analysis. This gives you much better and more information than you would get utilizing only your eye as a detector, and allows you to have surface analysis such as RMS available, and which becomes much more meaningful than peak to valley. And what I mean by that is if you have a high resolution interferometer and you are utilizing the analysis of using peak to valley, you are only analyzing 2 pixels on the surface. So it loses some of its meaning compared to a traditional test plate or Newton interferometer. And so the recommendation is, as you're moving to higher resolution interferometric measurement techniques, would be to move to a specification that captures more of the information across the entire surface. Traditional interferometry is great for getting most of the way there for most of the spherical surfaces. However, sometimes you can't capture all of the information on the surface. One of the methods you can do to take it, the next step is using stitching interferometry. This allows for both larger diameter and full aperture spherical coverage and aspheric measurements. This utilizes, again, typically a Fizeau or some type of interferometer and multiple subaperture measurements. And there's a diagram on the bottom left that you can see different circles. These are all stitched together to generate full aperture maps for either larger diameter spheres or A-spheres up to 100 waves of departure from a best fit sphere. These have the capability of measuring both convex, concave, flat parts, and high numerical aperture components, potentially up to full hemisphere. So it's another tool in the toolbox that allows for full aperture coverage. This is really important when you're utilizing deterministic subaperture polishing, because in order to create your dwell map, you have to have the information available in order to be able to create that dwell map. So you need full aperture coverage really to get a really good deterministic form convergence. Okay, so that was my quick, as I mentioned, quick summary of the fabrication and testing methods. Now I want to spend a little bit of time talking about optical manufacturing tolerances. And so some of the time, the questions we get, why tolerance? Why do we want to do this? Why can't I just hit default or just use the Optimax tolerancing chart and just pick a column and go? Well, the reason you want a tolerance is it constrains the amount of optical path difference fabrication induces to the system. And it's also the communication tool with the fabricators. I have very seldom see very many lens designers that stand over the shoulder of a fabricator to tell them what's happening. And so typically you need to have some type of tolerancing tool. And tolerances also influence the cost to manufacture an optic. Some tolerancing types will influence it more than others. But it really comes into, why do you want a tolerance? You want to optimize performance and you want to minimize cost. So what we're going to do today is we're going to use the Optimax tolerancing chart as a talking point. The Optimax tolerancing chart, for those of you who may not be familiar with it, is a tool of guidelines that we've created of what's possible for spherical optics to be made in 1 week. And what I'm going to do is the attributes on the left-hand side, I'm going to talk through each one of these, and we're going to use this tolerancing chart to aid in our conversation about spherical lens tolerancing. One of the first questions you get is, well, how much if I change this, and this, how much will it cost? Well, I can very quickly give you a guideline here. As you tighten the tolerances, it's going to get more expensive. However, that's not very satisfying of an answer. So what I'm going to do throughout the rest of the presentation is I'm going to give some specific examples and just some guidelines of why something might be more expensive. And so as you're tolerancing your next design, if you have the option to loosen one of those tolerances, it might help save some time. The other recommendation I will give over and over again, as soon as you have a design that you want to have fabricated, instead of shooting it over the bow, make sure you have a conversation with your manufacturer about what can we possibly do to reduce some of the cost here. And there may be some good suggestions that result. So let's start off with glass material. We talked about some of these properties already, and we talked about how optical glass is characterized by its index of refraction and Abbe number. And for most glass manufacturers, the materials can be a direct substitute. But be aware that the optical design code may not take into consideration any other properties other than optical properties. It will be up to the designer to consider chemical properties, thermal properties, spectral transmission, material quality, and mechanical properties. I have an eye chart here next to show two different glasses that have the same glass code. So they have the same, optically, according to their data sheets, they have the same index and Abbe number. However, I have a couple circles here that show that there's different temperature coefficients of refractive index. So if you remember what I mentioned briefly, that index will change as a function of temperature, this could may influence your system as a function if it's being exposed to different thermal gradients. There's also on here a difference between different hardness values. I didn't talk about it in a lot of detail in today's presentation, but hardness directly influences how fast a material will remove during the grinding process. And so this is something that from a fabricator's perspective may influence how the optic is fabricated. And so, of course, I mentioned, well, okay, so should I just pick the softer one? Because material removal is faster for softer glasses. Does that mean shorter processing time? Does that mean I get cheaper optics? No, not necessarily. There are several other factors that offset potential time savings. So just choosing the softer glass because it's going to remove material faster may not necessarily be the best thing. Soft glasses tend to actually be more difficult to polish to achieve both good cosmetics, that's scratch dig, and low RMS surface roughness, your surface form. Getting both of those at the same time. Soft glasses tend to pick up scratches much more readily than harder glasses. And as I mentioned before with test plating, same thing happens if you pick up a scratch with a soft glass. Worst time is to happen is when you're so close with the surface form. So in general, lenses with identical specifications, except for material, a BK7 or borosilicate lens will be cheaper to produce. And I mentioned before, they are often used, borosilicate glasses are often used as the baseline for looking at material cost. It's also for a lot of mechanical, thermal, chemical, pretty much every property. If you move away either higher or lower from BK7, it's probably going to be a little bit more expensive or more difficult to fabricate. Which is, I read my other slide a little too fast. Okay, so next, some of the design concerns with glass quality. Optical materials do the work in your lens system. Make sure that you fully understand why you're choosing them, and make sure you first and foremost you want it to perform. Performance is key, so you want to make sure that you're picking the optic with your optical material that will work the best in your system, and then the recommendation is index that with other attributes. Mechanical, look at the durability. Chemical, the robustness. Thermal, the temperament. Form of supply. This is often overlooked. If you need a lens that has either a larger diameter or is thicker than is available in that type of material, that's maybe more troublesome to get your hands on. Cost. What is easy for one manufacturer may not be as easy for another, and so cost may be a disparity. Then availability. Make sure to keep an eye on which glasses are discontinued or revised. This is something that doesn't usually happen overnight. It's usually on a much slower schedule, but if you're trying to repeat a design from 15 years ago, those glasses might not be still available. You might want to take another check. Optical manufacturers consider all these attributes when they're pricing the lenses. So anytime additional specifications are added to the material itself, it will add cost, but probably more important to most people is actually the lead time. The next step in our going through our table here is looking at lens mechanical dimensions. So when I talk about these, it's specifically talking about diameter, center thickness, which I refer to as CT, your overall height, and your sag. So some considerations for mechanical dimensions, again, very similarly, when you're looking at the first pass of an optical design, you might not necessarily care about the tolerance on your diameter or your thickness, but this is something that really is very important when you're trying to take it from an on-paper design to a prototype. Is that tight thickness tolerances are more difficult when combined with, and so as I mentioned before, a lot of these tolerances layer on top of each other. If you have very strict cosmetics, so your scratch dig, fractional wavelength irregularity, or soft optical materials. I talked about this combination before. These can be very challenging. If you have a few microns to work with for your thickness tolerance, and you're trying to hit fractional wave irregularity, and you have a soft material and you pick up a scratch, you have to keep removing material until you get through the scratch and hope that you're still going to keep your irregularity on your surface. It just usually an optician will take a look at that when they're pricing ahead of time, because they will more than likely have to add more material into the order because they know that their yield might not be as good if they have really tight tolerances like that. Thin edges. When I talk about thin edges, this is less than 1 millimeter thick. If at all possible, should be avoided. Thin edges are the site of a lot of chipping that can cause surface defects, or if worse, catastrophic failure, and also can be really difficult to hold during process and measurement. Try to avoid compounding or conflicting dimensions. An example, if we look over on the right-hand side, if your overall height depends on both your center thickness and your sag. So when I talk about avoid conflicting or compounding dimensions, tolerance what is important, and then after that, then use the others as reference. Your aspect ratio is the relationship between your diameter and your center thickness. A very high aspect ratio part may result in glass bending or flexing. A high aspect ratio part would be something that is extremely thin. Ideal aspect ratios are at least 6:1 for precision optics. And involve optomechanical design is early in the process to identifying mounting surface or established lens spacing. This can be a lifesaver later on, and having a conversation with your optomechanical designer and your fabricator to make sure that the tolerances are evenly distributed to essentially minimize the overall cost but maximize performance is a desired state. Your clear aperture. So clear aperture, this is where your fabricator needs some room to work. This allows for be able to hold on to the part during coating. Your polishing edge effects as you're polishing a material, whether it is a conventional polishing or if it's a sub-aperture polishing, as your tool goes over the edge of the part, your pressure distribution is going to change and you're going to have a slight edge effect that happens. There are ways to minimize this, but having a little bit more room allows for some flexibility in processing. It's also important to have bevels on the surface. A bevel or a chamfer helps protect sharp edges to minimize chipping on the surface. It's also something to keep in mind that if your optic is going to be in any type of an assembly at all, it is likely that it may have some type of obscuration or retainer obscuration. So knowing how much you need to account for that and also including your clear aperture different than your full aperture may be very helpful. The other recommendation we have is to tolerance clear aperture with linear units. You'll see, and I get this question quite frequently, that they'll say, well, Jessica, your olive and your tolerancing chart is all in percentage. Why do you have it in percentage, but then you're asking us to tolerance in linear units? And the reason for that is that it really does scale with size. A 1 millimeter clear aperture is a lot different if you have a 5 millimeter part versus a 300 millimeter part. So the recommendations we have are percentage because it scales with size. It's a lot easier to talk with, but the recommendation is to actually put linear units on the drawings. Next up is radius. So another question we get, should I tolerance with linear radius or power? The metrology used is the key difference. You're going to use a power tolerance that controls radius through increments of sag change relative to the test plate of known radius. So essentially, you're using a test plate to measure the power in calculating the radius. And there's a cartoon over on the right. A linear radius tolerance controls the radius in linear units relative to the normal. And there's another cartoon on the right as well. And radius is measured for this directly using an interferometer equipped with distance measurement capability. So in summary for this is that radius can be toleranced using either fringes of power or stated as a linear radius tolerance. And specifying one is sufficient and can be converted to the other. But if both are specified, we just want to know why. There may be a good reason, just let us know. One caveat here is power is still useful when tolerancing plano surface because a radius tolerance on a plano surface is meaningless. Surface irregularity. Okay, so we have three different sections here. It's irregularity using an interferometer, a profilometer, or a coordinate measuring machine, or CMM. I'm going to talk today just about irregularity with an interferometer. The reason for that is for a spherical optic, the majority of the time you're going to be using an interferometer. And what the surface irregularity is a measure of deviation from a perfect surface. And it's a function of both the optician's skill and the process geometry. When I mention about that is when I talk about multiple blocks. There's a photograph on the right. This is when more pieces are polished on the same lap. You'll have less irregularity than if you have with 3 spots or singles. And a lot of this comes from the edge effects that I talked about earlier, because as you move your lap off of the part, you're going to have a very pressure distribution and Preston's equation that removal rate is proportional to pressure times velocity. You want to keep all of those as even as possible throughout in order to keep a nice predictable removal rate. Another thing to consider, and I said I'd only mention this twice very briefly, this is the second time, is that mid-spatial frequency errors should be considered for sub-aperture polished surfaces. Surface irregularity is typically measured interferometrically or with a profilometer. Again, for spherical surfaces, usually this is interferometrically, and your specification must contain a value, band-limited RMS, robust peak to valley or PVR, or peak to valley over the clear aperture. Next up is wedge. So wedge is something that can directly influence your image formation. And this type of error can propagate through the optical system. Optimally, you want to have both your optical and mechanical axes co-located. And so there's a video going on the bottom left-hand side indicating what happens if that is not the case. So if this optic has wedge, and so when you're looking at it from the side, one edge thickness is going to be larger than the other. And so the description of edge thickness difference is the difference between your edge thickness at your maximum point, your edge thickness at your minimum point. So that is an optic that has wedge. So for a spherical optic, which is one nice thing about a spherical surface, is that you can do a post-process called centering or centration to correct for this in spherical optics that have been processed oversized. The middle of photograph there is actually an animation showing the centration process, where we're essentially moving the mechanical axis by removing material in order to have, again, the optical axis and the mechanical axis co-located. This is an option, and for spherical lenses that are processed oversized, as I mentioned before. For A-spheres, this is not an option, and this type of wedge has to be controlled in process. Scratch and dig or cosmetics. This is the single most powerful cost driver for fixed part geometry and material, and also one of the ones that is most often confused with surface roughness. Cosmetics are localized, non-periodic defects versus surface roughness, which is looking at the overall texture. So again, cosmetics are scratch and digs. And again, they're called cosmetics for a reason, is they may have little effect on system performance. So for example, if you a camera lens with a scratch on the end or on the last surface may actually have limited impact on the system. However, it doesn't look very nice. And so this is where it could play a role in the performance, but it may or may not. So it's something to really look at where in the design are you and how should you specify the scratch and dig. There's a lot of different applications that require very, very tight cosmetic tolerances, but not all of them. The recommended specification for this is ISO 10110 Part 7 with a 2017 revision. This includes both dimensional and visual comparison specifications. The upgrade, I will call it, in 2017 was the addition of the visual comparison method into the standard. Traditionally, it has had the dimensional measuring of the digs by area and scratches measured by width, but the addition was adding the essentially what the U.S. has been using for years, the MIL standard, in order to be able to quickly verify using a visual brightness method. And all the designer has to do is specify which comparison standard should be used. Next up is surface roughness. I mentioned earlier, surface roughness is the measure of the texture on the surface, and it influences the scatter in the optical system. And so controlling the surface roughness is important for a lot of systems. Typically, it's measured by surface profilers. A white light interferometer is the most common. There's a schematic diagram of one in the center there, and then on the right is a resulting phase map image. False color phase map image of polishing marks on an optical surface. So coding. I have one slide on coding. There's a lot of great references on codings, and I'm not going to spend a lot of time with it. However, because the majority of optical surfaces have some type of functional coding, I'd be remiss to at least talk about specifying these. When you're specifying them, you need to specify the desired transmission or reflection requirements, the wavelength bands of interest, their angle of incidence, and other aspects to consider include polarization requirements, laser damage threshold, witness sample requirements, your coding aperture, and environmental requirements. And I have here, and I'm assuming you're going to be able to have the slides later, is an example coding specification. So in my last couple slides, I want to talk about the lens drawing and communicating your design. It is the fundamental communication tool. This is how you tell your fabricator what you want to have made, how you want it measured, and what features are the most important to you. And my recommendation is use a standard template. ISO 10110 has one of these, but no matter what you're using, my recommendation is be clear, be concise, and be consistent. the ISO 10110 is an international standard for optical drawings. These are available for purchase through ANSI. And I'm going to now move into my most confusing slide that I have for the entire day. But why I want to highlight this is because all of the information that we walked through and talked about today, on the right-hand side is the tolerancing chart, on the left-hand side is an example drawing. And this is adapted from a really great reference paper and poster. I have the reference below, where they walked through translating the American mill drawings to ISO 10110. And so a combination of what we talked about today, of what some of the tolerances might be to reduce some of the cost, the international drawing standard, this tells you how to put it onto a piece of paper to make it clear, concise, and consistent for your manufacturers. And if you're new to using the ISO 10110 drawing format, I recommend there is the Optics and Electro-Optics Standards Council, as part of ANSI, has accredited training courses that go through and to walk you through how to create one of these drawings. The last two things before I summarize is reviewing a case study that I worked with Rich Youngworth and Dave Akins 10 years ago now. But even though it's 10 years old, it still highlights the importance of considering cost and design. What we did is we took a case study design. It was not a complete design. There was no optical mechanical considerations, but we took a set of 5 tolerances. We looked at representative lens design defaults, your ISO 10110 defaults, commercial precision and practical limit at the time. That's what our optical tolerancing chart was here at Optimax. And then we provided price functions versus tolerance, and took a look at how did performance and cost play a role in the entire system, looking at this case study. And we still concluded that cost is important to consider in tolerancing. And what the results were is in this plot here. This shows on the left-hand axis is the predicted RMS wavefront error, or the performance. And so lower is better for the performance on this one. So you want to be as low as possible. You want to minimize your wavefront error. And then on the right-hand axis is the relative cost factor. So again, this is your cost, and you also, so low is good here. So you want them both to be pretty low. And what we found is that the defaults in the ISO 10110 and the commercial case, they had fairly loose tolerances. So the performance wasn't that great, but your costs were all pretty low. But moving from the commercial to the precision, the lines crossed. And so you started to get a little bit higher cost, but your performance got quite a bit better. And then if you tighten every single knob there is to tighten and do the manufacturing limits at the time, your performance was great, but your cost skyrocketed. And the Custom 2 and the Custom 3, where Dave and Rich going through and doing some tolerancing analysis based on their experience, and then also looking at the cost functions, and found that the best solution incorporates both performance and cost. And so it's something to definitely consider with tolerancing. So tolerancing does involve trade-offs. So a summary, as I can conclude today, of a few of the cost drivers. Cosmetic tolerance, your scratch dig, is a huge cost driver, especially once it's below 60/40. Small clear aperture relative to the diameter is challenging from a number of different perspectives, and can add cost, as well as a tight radius and irregularity. A chemically stable material may be a lower optical performance, but the fabrication may be cheaper. And high aspect ratios, thin edges, and exotic perimeters are possible but costly. And so just a couple general thoughts. My recommendation is to learn from others' experiences, ask your peers and mentors after consulting past examples. Remember that value is not the same thing as price. Just because an optic is expensive does not necessarily mean that it's going to work the best in your system. So what's the most important for your system? And again, make sure you talk to, as my next slide, or next point talks about, talk to your vendors and your suppliers, talk to other peers, and to find the optimal solution. And again, the optics industry is really small, very niche field. Find whose capabilities best match your needs, and make sure to establish relationships with those individuals. So today was definitely a whirlwind of high-level information. I feel like I only touched the surface on a lot of different topics. There's additional resources for more detail. Optimax has a lot of online resources. There's our link to our website, some of our technical papers. ZMAX also has online resources as well. There could be future webinars. I let ZMAX or myself know what topics you want to hear about. The A-spheres and or freeform manufacturing tolerance considerations might be one of them because they were not mentioned at all in this one. There's also a small plug for myself, an in-person short course. I'll be teaching a 4-hour short course on optical materials fabrication and testing for the optical engineer this August at SPIE Optics and Photonics. So I go into a lot more detail on a lot of the different topics that we discussed here today. I also want to mention ZMAX, their Envision 2019. Their conference will be held in October in Boston, Massachusetts. And with that, I will conclude and say thank you, and then turn it over to Chris, who I think will moderate the Q&A session.
Yes, thank you very much, Jessica. That was excellent. A huge amount of very valuable insights in there, and we'll definitely have to have you back to talk about some of those A-sphere topics as well. So yes, please do. You should find on your GoToWebinar there's a small question section. Please type your questions in there if you have any for Jessica. We've got a couple already, so I'll just move on to these. So the first one is from Kyun, I think, asking because you mentioned earlier, Jessica, there are catalogs obviously from different manufacturers of different glass types and preferred glasses for manufacturers as well. Mm-hmm. Are there similar catalogs available for standard plastic materials as well?
Yes, and so a lot of the plastic materials, they come right from the plastic optics manufacturers themselves, but there are fewer. The number of plastic materials available is, in numbers wise, is smaller for plastics than they are for glass. But those do exist, and obviously there was nothing about polymers or plastics in this presentation, but there are a lot of great companies that have great online resources available for that information.
Okay, we've got 2 people asking, will the presentation be available for download and the slides available for download? The webinar is being recorded, so this recording will be available on our website. And then in terms of the presentation itself, Jessica, I believe a PDF will be available. Is that? Could you?
Yes, that should be fine. Yes. Mm-hmm.
Okay. So we've got those 2. Bear with me a second. Another one is we have from Shui, which is what is robust PVR? I think you mentioned that.
So robust PVR is it's a technique. There is an excellent paper by Chris Evans that wrote a paper on robust PVR, and I can actually give the link to it to Chris to put with to answer that question. But what it takes is it uses the Zernike residual RMS and minimizes the effect of residual, or I would say spurious errors that can result with a traditional peak to valley measurement. As I mentioned before, when you're just using 2 values or 2 pixels, if you have a piece of dust or if you have a bad pixel or a hot spot on your transmission sphere, it may cause an error in your measurement. So this takes also in the looking at the Zernike residual RMS as well. And I can't remember the calculation exactly off the top of my head, but I do know that any MetroPro application has the ability to analyze it very, very easily, but I can also supply you with the reference paper. But Chris Evans is the author of that.
Cool. Lots of thank yous on here, and lots of things coming in thick and fast. Just bear with me a second. The next one is tolerancing single lenses is one thing, a lens stack assembly is another. Is interferometry also a valid tool for judging lens assemblies? maybe outside the scope.
Yeah, So that would be more of a system test,
Yeah.
and it really depend. It would depend on the system if it's even possible.
Okay. Bear with me a second. So, how do you process the fringe informations from an interferometer for optical surface analysis? To be honest.
So I didn't go into this at all. So typically, for spherical interferometers, we would use a commercial analysis software. So both whether it's a Zygo interferometer or if it's a 4D interferometer or whatever other. There's many other brands of interferometers as well, but we would use a commercial software to analyze those. In terms of the math behind it, I could go. That's another topic for a different day.
Okay. Okay. Here's one. In a piezo interferometer, what is the reference piece? Is it the ideal shape of the part under test, or is it a flat?
So for a spherical surface, it would be a transmission sphere. So it would be a spherical wavefront, and so with a sphere, it would be a spherical wavefront, and for a flat surface, it would be a flat wavefront or a transmission flat.
Okay, great. Then from Vincent, we have, hi Jessica, do you have any resources on CMM, which is coordinate measuring machines?
Yeah, so that is actually a topic that is covered in freeform. When I talk about freeform fabrication and processing, the coordinate measuring machines are used very frequently for any time you need to not only give something that's non-spherical or non-rotationally symmetric, but you also need to incorporate other mounting or features into the system. And with freeforms, that's an issue. And there's different I would say precision levels of coordinate measuring machines as well. There's a lot of them that are your larger standard machines that can have precision down to, or accuracy down to 1 micron. However, then there's also the UA3P type of high precision profiler or coordinate measuring machine that gives you a little bit higher precision data as well. But there's a lot of references, a lot of things on that, but that is something that typically is I personally talk about more when I talk about freeforms.
Okay, great. And then one came in a while ago that I missed. Was from Fatima. Thermal lensing is a problem for high power lasers. Is there any kind of tips or restrictions that you should be aware of when choosing? I'm assuming it's choosing materials or.
Yeah. So that yes, I've actually, those were some of the slides that I took out. I was actually talking about thermal lensing. I'm sorry, in order to be able to fit into the time here. So thermal lensing, yeah. So that could be balanced a number of different ways. Whether sometimes it's scanning across the surface, it could be choosing your material, or sometimes people use almost like a heat sink, thermal sink to pull stuff out. But it's especially with your higher power lasers and systems that's going to be an issue. The other big thing to really consider also is make sure that you minimize absorption in the material as well, both through the quality of the material, but then also making sure that the manufacturing processes, both in the fabrication, the cleaning, and the coating, minimize the amount of absorption, because that's where the absorption and the heat buildup comes in.
Okay. Excellent, thank you. I've got one here about irregularity from Benjamin. So if you're tolerancing to using the ISO 10110 standards, I believe it's, well, how do you, specify the C tolerance on it? I think it's the C, rotationally symmetric irregularity, I believe.
Okay, yes, yeah. So that would be, so that kind of falls into, I didn't go into a lot of detail into this. Again, that might be better for an offline conversation, so I have a little bit more context on that. But I mean, it would be similar to tolerancing irregularity. I think I might need more context on that question.
Okay. So yes, Benjamin, if you would like, yeah, you've got Jessica's email address there. Maybe it's a good good chance for an offline conversation to send that.
Yep.
And then we've got a few thank yous coming in, and then there's a good question here from Saran, and then I think we might have to wrap up. So apologies if we didn't get to your question. What kind of characterization is used for the reference materials for interferometry? So the references.
Yeah, so that is something we do use a lot of times. So the transmission spheres are also the individual elements are characterized interferometrically as well. But then we also do tests of the system as well. So there are interferometric measurements. The other thing that we also like to make sure that we at least do here at Optimax is that we have multiple different measurement methods to characterize the same surface, and so that we can test and calibrate one to another to make sure that we minimize the measurement error. Because as I mentioned from my slide about Daniel Malacara, you can only make an optic as good as you can test it. So we want to make sure that we have redundancy in measurement. But when you're making the transmission spheres, you are using interferometric measurements to measure the surfaces, but then you do a full system test.
Okay, excellent. So thank you. I think we've got through a lot of questions there. So one maybe very final one from Nasir. Is there a good resource for the nitty-gritty details of fabrication?
In terms of a book, I'm not sure off the top. There's a lot of different books. I have a whole list of references. However, I mean, actually, I teach a full course on this at the U of R, so that might be. But there's a lot of different books that each have some really good key information in it. So I guess it really depends on which aspect of the fabrication that you're looking to get more information on.
Okay. So thank you very much, everybody. Thank you for your input and your questions. I've just sent my email address to the audience. So if you do have any webinar ideas for future, please do contact me. Anything you'd like to see, that's ZMAX or Optics Studio specific, or any of these joint webinars, that would be excellent. Just to reiterate what Jessica said about Envision, registration is open for our Envision in Boston in October. Please check out our website, the events page. We've put the agenda up there. There's already some great presentations lined up from optics leaders. Some really important insights from people like our CEO and our founder, Ken Moore. And there'll be some great workshops in there to teach you extra skills with using our tools as well. So please check that out. Other than that, thank you so much, Jessica, for sharing your insights, and thank you everyone for attending. Thank you, and have a good night, good morning, or good afternoon, wherever you are. And thank you very much, Alma.
Thank you.